All right, talking a little bit about bits versus symbols, we learned that a stream of pulses occupies a bandwidth of RP to 2RP, where RP denotes the pulse rate and the bandwidth of, or actually I'll say that the RP relates to 1 over TP. And if you're wondering why is it in between, well, if you look at this, if alpha 0, this is simply, right, this is simply 1 over TP. And if alpha is 1, then this would be 2 over TP, right? So that's what we're looking possibly between is 1 and 2 over TP. And it depends upon the pulse shape. In binary modulation, each pulse represents a bit. However, as we talked before, pulses can also represent a symbol. And this is important because each pulse has a fixed bandwidth. And we go back to this idea that I have my symbol, right? It has a fixed bandwidth, but the number of bits that the symbol can transmit depends upon my modulation. Okay, so the idea is we have a fixed bandwidth which depends upon our repetition rate. It also depends upon alpha, and that is the symbol. So each pulse we're sending represents a symbol, but depending upon the modulation architecture, it could have any number of bits that are associated with that. So I want to talk a little bit about bandwidth efficiency because this is what it all comes down to and why we care about this. If we assume we're sending RP Nyquist pulses per second, the signal occupies a bandwidth of RP hertz, as we just discussed. And so that's one pulse being transmitted RP times per second, and so we have RP hertz as our bandwidth. But each pulse represents one symbol. So basically, the pulse is what we're sending physically, but in reality, in our modulation scheme, it's actually a symbol. And so in binary modulation, each symbol represents 1 bit, so we're transmitting 1 bit per second per hertz. But if we can improve the spectral efficiency by transmitting more bits per symbol, because each symbol has a fixed bandwidth, if we can increase the modulation complexity, then we can increase the number of bits transmitted. And in an M-ary modulation, each symbol, or you could say pulse, right, represents k bits. So you end up with a spectral efficiency of k bits per second per hertz. And once again, this goes back to the same idea that our bandwidth is determined by our pulse, not by the number of bits. The way we get more bits per pulse is we just basically have more states, if you will. And I'll just draw you a real quick cartoon. You can think about it if I had a pulse that was this high, and a pulse that was this high, and a pulse that was this high. Each one has the same bandwidth, but they represent 3 different heights, and so 3 different pieces of information. And so that's how we can get to a much higher spectral efficiency, meaning how many bits are you transmitting for a given bandwidth.